Hi, I'm Chanyoung, a PhD student in the School of Computing at KAIST. I'm a member of the Big Data Intelligence Lab led by Professor Joyce Jiyoung Whang. I'll present our paper, Running Representations of Bi-Level Knowledge Graphs for Reasoning Beyond Link Prediction. A knowledge graph represents human knowledge by defining the relationships between entities using triplets. For example, the fact George Clooney acts in the movie Ocean's 11 can be represented as a triplet. George Clooney acts in Ocean's 11. Knowledge graph embedding aims to represent the entities and relations as embedding vectors. Most existing knowledge graph embedding methods focus only on the relationships between entities. However, there can be meaningful relationships between triplets in real-world knowledge graphs. For example, let's consider two triplets, T1, Joe Biden holds position Vice President, and T2, Barack Obama holds position President. To represent the fact that Joe Biden was a Vice President when Barack Obama was a President, we define a high-level relation works for, which defines the relationship between two triplets, and also define a higher-level triplet, T1 works for T2. In this paper, we define a bi-level knowledge graph that includes both the base level and the high-level triplets, where the base level triplets represent the relationships between entities, and the high-level triplets represent the relationships between the base level triplets. For example, in this figure, these base level triplets are the triplets contained in the conventional knowledge graph FB15K237, and these high-level triplets represent the relationships between the triplets. Using bi-level knowledge graphs, we can represent richer information which can benefit many downstream tasks. Using the bi-level knowledge graphs, we can consider more complicated reasoning tasks than link prediction. First, we define triplet prediction as the problem of predicting a triplet that is likely to be connected to a given triplet via a high-level relation. For example, given the fact Beckham has nationality England, we predict which triplet can be connected to this fact, and the answer is Beckham plays for England national football team. We can represent this problem as triplet prediction in the form of angle bracket, parenthesis, Beckham has nationality England, parenthesis, prerequisite for question mark. Second, we can think of conditional link prediction, whose goal is to predict a missing entity in a triplet conditioned on another triplet. For example, if we want to know who was the president when Joe Biden was the vice president, we can formulate a conditional link prediction problem by angle bracket, parenthesis, Joe Biden holds position vice president, parenthesis, works for, parenthesis, question mark holds position president. Our contribution can be summarized as follows. To the best of our knowledge, our work is the first work that introduces the higher-level relationships between triplets in knowledge graphs. We define bi-level knowledge graphs and create 3 real-world datasets. We propose an efficient data augmentation strategy using random walks on a bi-level knowledge graph. We develop Vibe to learn embeddings by effectively incorporating the base level, the higher level, and the augmented triplets. We propose 2 new tasks, triplet prediction and conditional link prediction, which have never been studied. We show that Vibe significantly outperforms 12 different state-of-the-art knowledge graph computation methods in these new tasks. A conventional knowledge graph, which we call a base level knowledge graph, consists of a set of entities, relations, and triplets. Given a base level knowledge graph, we define a set of high level triplets, which represents the relationships between the base level triplets using the high level relations. Let R hat denote a set of high level relations and H denote a set of high level triplets. We define a bi-level knowledge graph by adding high-level triplets and high-level relations to the base-level knowledge graph. We create three real-world bi-level knowledge graphs named FBH, FBHE, and DBHE by defining the higher-level relations and triplets. FBH and FBHE are based on FB15K237, and DBHE is based on DB15K. FBHE and DBHE contain some externally sourced knowledge. Here are some examples of high-level relations and high-level triplets in FBHE and DBHE. For instance, the first example represents the fact that for the King's Speech to win BAFTA Award should nominate the King's Speech. Among the high-level relations, works for succeeded by in FBHE and next alma mater in DBHE were made by externally sourced Wikipedia articles. Real-world knowledge graphs are very sparse, and there are many missing triplets in the graph. We propose a data augmentation strategy using random walks on bi-level knowledge graphs. The goal of data augmentation is to add plausible triplets that are missing in the original training set. To identify plausible triplets, we conduct random walks. Specifically, from an entity, we randomly visit one of its neighbors by following a base level or a higher level triplet. Let us consider a random walk path that consists of entities, relations, and higher level relations a random surfer steps on. For example, this random walk path consists of H0, R0, HI, RI, R hat, RJ, TJ, and here R hat indicates a higher level relation. To trace the patterns of random walks, we define the relation sequence pk as a sequence of relations and higher level relations extracted from a random walk path. For example, a relation sequence of R0, Ri, R hat, and Rj is extracted from this random walk path. Then we define the confidence score of a relation sequence pk and a relation R, which is the probability that the entity pair connected by the relation sequence pk is also connected by the relation R. If the confidence score is high, it indicates that the entities connected by pk are also likely to be connected by R, and thus we connect those entities by R and these triplets are added to the training set. This figure shows an example of the augmented triplets in FBHE. Since the confidence score of pk-R is greater than a certain threshold, we added the triplet UCLA Bruins men's basketball plays basketball. We observed that our random walk-based data augmentation strategy effectively adds many missing triplets. We propose Bi, a knowledge graph embedding method reflecting the structures of the base level triplets, the high level triplets, and the augmented triplets. Given a bi-level knowledge graph, Bi considers these three different types of losses. Let me explain the details of each of these terms in the following slides. The loss of the base level triplets, L-base, is identical to a standard knowledge graph embedding loss function. Here, G is a soft plus function and function F is a knowledge graph embedding scoring function. We can use any knowledge graph embedding scoring function for F. In our implementation, we used quad E for vibe Q and BiQ for vibe B. To define a loss incurred by the high-level triplets, we represent an embedding of a triplet Ti which consists of Hi, Ri, and Ti by concatenating the embeddings of Hi, Ri, and Ti and projecting it using a learnable projection matrix W. Then the loss of higher level triplets L high can be represented in this form, where the bold-faced R hat indicates an embedding of a higher level relation. Once we represent an embedding of a triplet, the way we compute the loss incurred by the higher level triplets is similar to how we represent the loss of base level triplets. Since we added triplets by our data augmentation, we also compute the loss incurred by the augmented triplets, which is LAUG. Finally, we define the loss function of Bi by combining three loss terms, L-base, L-high, and LAUG. Here, lambda 1 and lambda 2 are hyperparameters indicating the importance of the higher level triplets and the augmented triplets respectively. We can solve triplet precision and conditional ring precision problems using Bi-Level. First, to solve a triplet precision, for example, angle bracket, ti, r hat, question mark, Bi-Level computes FTP-X in this form for every base level triplet X in each train, and then predicts the answer to be the triplet associated with the highest score. To solve a conditional ring prediction problem, for example, angle bracket, ti, r hat, parenthesis, hj, rj, question mark, Bi-Level computes FCLP-X in this form for every entity X in V, and then predicts the answer to be the entity with the highest score. Here, this term considers the base level triplet, and this term considers the high level triplet. We use 3 real-world Bi-Level knowledge graphs. Among these, FBH and FBHE share the same base level knowledge graph. FBHE contains more higher level relations than FBH. We split the base level and the high level triplets into training, validation, and test sets with a ratio of 8 to 1 to 1. Around 10 or 12% of the base level triplets are involved in the high level triplets. We compared Bi-Level with 12 different state-of-the-art methods including string matching, pathfinding, rule, relation path, and latent space-based models. We repeated experiments 10 times for each method and reported the average. This table shows the results of triplet prediction. Our models, Bi-Q and Bi-B, significantly outperform all baseline methods in terms of all metrics on all datasets. We observed a significant performance gap between the best baseline method and Bi-Level. This table shows the results of conditional ring prediction. Again, our models Bi-Q and Bi-B significantly outperform all baseline methods in terms of all metrics on all datasets. We show some examples of conditional ring prediction in FBHE and the predictions made by Bi-Q. In this example, even though we have the same problem, Jojonas is a question mark, the answer becomes different depending on the following triplet. In the first problem, we say, Jojonas is an actor because Jojonas is a voice actor. In the second problem, we say, Jojonas is a musician because Jojonas is a singer-songwriter. On the other hand, the answer can be different depending on the conditioned triplet. In the first problem, we say Saturn Award nominates Avatar is a prerequisite for Avatar wins Saturn Award. In the second problem, we say Academy Awards nominate Avatar is a prerequisite for Avatar wins Academy Awards. In terms of typical base level link prediction, Bi-Level models show comparable results to the baseline methods. Our Bi-Level loss function does not degrade the performance of conventional link prediction. Different from the baseline methods, our Bi-Level models have the extra capability of dealing with the triplet prediction and conditional link prediction tasks. This table shows some examples of the augmented triplets on FBHE and DBHE. The higher level relations are marked in purple. We can see that there exist considerable overlaps between the augmented triplets and eValid and eTest. Our augmented triplets include many ground truth triplets that were missing in the training set. In this paper, we defined a Bi-Level knowledge graph by introducing the concept of the relationships between triplets. We proposed a random walk-based data augmentation strategy to add missing plausible triplets. Our proposed method, Bi-Level, takes into account the structures of the base level triplets, the high level triplets, and the augmented triplets. Experimental results show that Bi-Level significantly outperforms state-of-the-art methods in terms of the two newly defined tasks, triplet prediction and conditional link prediction. We believe that our method can contribute to advancing many knowledge-based applications such as conditional QA and multi-hop QA. Our datasets and codes are available at our GitHub. If you have any questions, please let us know. Thank you.